Hello, everyone. Yeah, just give me one second. Hello, everyone. Welcome to this class on CMOS driver design as part of the EE 279 AS Winter 2025. So before talking a little bit about the CMOS driver design, first let us talk about a typical MOS transistor, which could be either a N-type MOS transistor or a P-type MOS transistor, such as the NMOS and the PMOS. So here I've shown the typical structure, a typical structure of what the devices actually look like on the silicon. So here you can see this would be actually an NMOS. It has an N minus, N plus region as shown here, which act as a source and the drain. And then between between the two N regions, there is basically a P-type material or P-type well, which acts as the body of this transistor. And then in between the source and the drain, there is also oxide layer, and on top of which there is a gate electrode. And similarly, you have the reverse in the case of the PMOS. You have the P plus P minus source and drain with the N-type body. And similarly, you have some oxide capacitor, oxide thickness here with a gate electrode. So the basic principle of operation of this transistor is, in the case of the NMOS, when the gate to source voltage, or the voltage between gate and source is positive, then what happens is the NMOS actually begins to attract electrons towards the surface of towards the interface between the transistor's channel, which is the region between the source and drain, and the oxide. And these electrons, which are attracted towards the surface, basically end up shorting the two N minus regions so that the two source and drain regions become shorted and therefore begin to conduct, and hence the transistor is said to be turned on. Similarly, in the PMOS case, you have the reverse. If the gate to source voltage is negative, then what happens is the negative gate voltage begins to attract positively charged holes towards the interface between the silicon and the gate oxide. And this ends up creating a P-type channel that shorts the source and the drain. Thus, the transistor becomes on. So, so if you consider when the transistor actually is set to be on, at what voltage does the transistor actually turn on, we can define a certain voltage called as a threshold voltage for the NMOS and PMOS. And we find that when the gate to source voltage of the NMOS is greater than the threshold voltage of the NMOS, it is on. And similarly, when the gate to source voltage of the PMOS, which is a negative value, is lesser than the negative threshold voltage of the PMOS, then it is said to be on. And basically here we are saying that the gate associated PMOS is more negative than the negative threshold voltage of the PMOS. And so under this condition, when this voltage condition is met and the transistor is switched on, if you know from basic device theory, device physics, we find that the once the transistor has been switched on, the current between the source and the drain is just given by this expression. So, for example, the source drain current in the NMOS is the mobility of the electrons times the oxide capacitance per unit area, which is just the dielectric constant of the oxide over the thickness of the oxide, times width of the NMOS, over 2 times length of the channel of the NMOS, times the VGS minus basically the gate to source voltage minus the threshold voltage to the power of some alpha, and this VGS minus the threshold, which is the excess voltage beyond the threshold voltage that causes the transistor to switch on, is called as a gate overdrive. There could also be other second order effects, which is what I've shown here. There could also be some dependence on the drain to source voltage, which is called as channel length modulation when the transistor is on or in inversion region. But we are not really going to consider this second order effects in our analysis. And usually this power here, so this alpha and beta, can be any number between 1 and 2. And it usually depends on the kind of transistor that you're talking about. Is it a bulk transistor? Is it a FinFET, and so on? It also depends on the channel length. So typically, when the channel lengths are shorter, basically these alpha and betas would be closer to 1. When you have a long channel MOSFET, when the channel is very long, it tends to be closer to 2. So now that we've understood basically the structure on silicon itself, how the NMOS and PMOS actually behave and work, let us now talk more symbolically. So the NMOS is symbolically represented by the symbol showing the gate, the source, and the drain. And basically, the threshold voltage is positive. Well, the PMOS has the gate, source, drain, but there's a little circle that is put on the gate telling that it is the PMOS. And in this case, the threshold voltage is negative. And as we discussed earlier, when VGS for the NMOS is greater than the threshold voltage, it turns on. And similarly for the PMOS, when the VGS of the PMOS is more negative than the negative threshold voltage of the PMOS, it also turns on. And we have already talked about the gate overdrive and also the basically the current between the source and the drain when the transistor operates in the saturation region. Now, for the CMOS applications, for what we are going to talk about, which is designing a digital driver to drive the channel of the link. We are going to basically assume that the transistors operate in saturation, and therefore the current is typically given by these expressions without any dependence on the source drain voltage. So now what is CMOS? So CMOS is basically a combination of PMOS and NMOS. And what happens is by using a combination of a PMOS and NMOS in a suitable topology, we can make any logical component. We can build any kind of digital logic circuit. So we can end up building a NOT gate, an AND gate, a NAND gate, and so on. And therefore, any kind of digital circuit for any kind of application can be built just by connecting the PMOSs and NMOSs in different topologies. So what does that typically look like? For example, here you see the PMOS is connected on top and the NMOS on the bottom, with the drain of the NMOS connected to ground and the source of the PMOS connected to VDD, and the drain of the PMOS and the source of the NMOS are shorted to the output, and the gates of the two transistors are shorted to the input. This you can clearly, and this would basically behave as a NOT gate, as we will see. And similarly, you can have another topology like this, which has the PMOS and NMOS connected like this, and this would behave more like an AND gate. And you can see how this works. For example, the red indicates a 1, basically a high input, and the 0 indicates a low input. Remember, these are for digital circuits, and therefore the inputs and outputs are discretized, are basically digital. They can either have a state of 1 or a state of 0, which corresponds to the highest voltage and the lowest voltage. So in the case of the inverter, which is what I've shown here, you can see when the input is a 1, the NMOS turns on while the PMOS turns off, because the gate to source voltage of the NMOS is more positive, while the gate to source voltage of the PMOS is less negative than the negative threshold voltage of the PMOS. So the PMOS is off and NMOS is on, and therefore the output is essentially connected through the NMOS to the ground, and therefore the output goes low. Similarly, you have the reverse happening when the input is low. In this case, the PMOS is on and NMOS is off, and the output goes high. So this is basically this topology of connecting the PMOS and NMOS is basically inverting the input signal. When you have an input of 1, it gives an output of 0. If you have an input of 0, it gives an output of 1. So this behaves as an inverter. Similarly, you can see this how this topology would operate. In this topology, say the input A is now 1 and B is 0. So if A is 1, B is 0, then the PMOS here is off while the PMOS here is on. And similarly, the NMOS, one of the NMOS is on, the other NMOS is off. So overall, you see that the PMOS is on. Overall, you see that the output is connected to VDD, and therefore the output goes high. And similarly, however, if say A and B are both 1, if A and B are both 1, then both of these are high, and therefore both the PMOSs are switched off, while both the NMOSs are now on, and therefore the output goes low. And you can work out in this particular topology that the output goes low only when both the inputs are high, and in any other situation, the output is basically high. So this behaves as a NAND gate. So why are we actually discussing the digital circuits is because we want to focus on using a CMOS inverter to build the transmitter and receiver of our basically our digital link for the data transmission. So what does this look like? We're going to have, remember, we are communicating between two chips. And therefore, imagine now there's one chip 1 and a chip 2, and there is a link that connects them through which you need to send the data. And on the input side, you have some digital logic at the input side, which is basically some digital circuit which supplies the digital data to the transmitter, and the transmitter essentially drives this link. And then finally, the signal goes to the receiver, and the receiver takes this signal and then sends it to the output digital logic, which could be another any digital logic in the chip too. So if you draw the circuit schematic of what this looks like, and we are going to design this transmitter and receiver using an inverter, using a CMOS inverter. And as we discussed before, this is basically our CMOS inverter. So what this will look like in the circuit domain is you basically have some input digital logic here supplying basically the shorted gates of the PMOS and NMOS. And this inverter is now driving this transmission line, which has an RLGC. And finally, this goes to the shorted gate of the inverter and on the chip 2, which then supplies to some output logic. So now you can see how this, intuitively how this driver would work. So imagine you wanted to transmit a signal of 1. So the input to the first inverter on chip 1 would go high. And if it goes high, the PMOS here is off while the NMOS is on. And therefore, what you find is that this node is now connected to ground through the on resistance of the NMOS. Remember that transistors, even though when they are on, there's the channel is conducting and shorts the source and the drain. The channel itself is a very thin layer near the interface of the oxide and the silicon. And because the very thin layer, it tends to have some resistance. And there's also many other causes of resistance, not only because it's thin, but also because there could be scattering at the oxide silicon interface. So there would be some on resistance. So when the input is high, this node at the output of the first inverter is just connected to ground through the on resistance. And therefore, now this signal that is 0 is now going to propagate along this transmission line at the basically at the speed of light in that particular waveguide, which is going to be C over square root of effective dielectric constant in this waveguide. And finally, it's going to go here. It's going to be a 0. And this is going to basically turn the PMOS on and NMOS here is off. And so the output, which is basically going to the next stage of the digital logic, is now going to go high. So you've essentially transmitted the signal 1 here all the way from chip 1 to chip 2 by using these two inverters which are connected to this transmission line. And similarly, you have the reverse happens when you have an input of 0. So input of 0, PMOS is on. This terminal is connected now to VDD through the on resistance of the PMOS. And so now the signal 1 is going to propagate. And similarly here you have the NMOS is on and PMOS is off. So the output is now going to turn low. So essentially the signal 0 has been transmitted all the way from the chip 1 to chip 2 using the transmission line along with the two inverters. Before we proceed, some important terminology about digital signaling. So let us say this is the actual signal that is transmitted. So this is the voltage fluctuation. This is the actual voltage that you would measure at, say, this terminal, which is the input terminal of inverter 1. And this, let's say this is the signal that is finally received at the output. So this red one would be the signal that's received at the output of the inverter in chip 2. So what you will find is that let's look at first the signal at the transmitter side. You will see that the signal usually does not rise very sharply, but tends to have some kind of slope. And the time it takes for the signal to go from 10% of VDD all the way to 90% of VDD, with VDD being the maximum voltage, is called as a rise time, excuse me. And similarly, you have something called as a fall time, which is the time it takes for the signal to go from 90% VDD to 10% VDD. And typically, the rise time of the signal and the fall time of the signal determine the bandwidth of the signal. In fact, you need to design the link in such a way that it can support frequencies up to 1 over the rise time or 1 over the fall time. So now, what happens to the signal which is found at the output of receiver 2? The signal is obviously going to be delayed. And this delay is because of the fact that it takes a certain time. So if you see here, once the signal here transitions, it takes a certain time for one of these transistors to switch and then the signal to propagate along the transmission line and then cause the transistors here to switch. And so it takes some time for the signal to propagate all the way from this node to this node. And because of that, you see that the input signal is now shifted in time at the output. And this shift in time, so basically if you consider here, if you look here, this shift in time in the signal and how you define this is you see where the signal crosses 50% VDD. So the original signal crosses 50% VDD around this location, but the new signal is now shifted in time by this amount to go to zero point 0.5 VDD. And this amount of shift in the signal is called as a propagation delay. This being the propagation delay in going from the low to high. There's also a propagation delay in going from high to low, which is basically, imagine there's a 50% here. So the time 50% here and 50% here, there's also a propagation delay to go from high to low. And typically the overall propagation of the signal, propagation delay of the signal is taken as the average of the propagation delay to go from low to high and high to low. So remember now our link here. So this is our link. And now if you look at the equivalent circuit of what the link looks like, especially for the if you look at the driver itself. So we have this long transmission line, and then this long transmission line terminates at the inverter on chip 2. But looking into the input side of the inverter at chip 2, it is just going to be two capacitors in parallel. It's just going to be the parallel combination of the PMOS capacitor and the NMOS capacitor. So it just ends up being some kind of load capacitance that is to be driven. So looking into basically looking out of the transmitter, what we see is basically some Thevenin equivalent impedance that needs to be driven by this inverter. So we are now looking at the single inverter at the transmitter side is just driving some impedance Z that has to be driven by this transmitter. Now, if you look at, so here I've shown basically a diagram of what the inverter typically looks like on silicon. So you have the NMOS here and the PMOS here, and this is typically what the layout of the inverter looks like. So this is the PMOS and this is the NMOS. And if you notice, the PMOS is always around twice as wide as the NMOS. And the reason why this is done will be described in the next slides. So now, let us study this inverter more in detail to understand what are the time delays involved when the input has a low to high transition versus a high to low transition and so on. So imagine now the input is transitioning from low to high. So when the input was originally low, the output would have been high, which means that the PMOS was on and the NMOS was off. Now there is a transition, and therefore the signal is going from a low to a high at the input. So when the input transitions from a 0 to a 1, the transistor, the PMOS, which was originally on, is now going to turn off, and the NMOS, which was originally off, is now going to turn on. And therefore, this node that was originally connected to VDD is now suddenly going to be connected to ground through the on resistance of the NMOS. So this is the equivalent circuit. So the impedance Z, which was originally at VDD, is now going to be connected to the ground through the on resistance of the NMOS. And therefore, the output node is now going to transition, going from VDD all the way to 0. And so you can, and because this transition, essentially because this so-called discharge of this voltage happens through this resistor, we can say that the speed at which this process of connecting this VDD node all the way to ground is often called as pull down, because the node is being pulled down to ground. And and if you look at this kind of discharge, it's very easy to see that the speed at which this pull down happens is going to be proportional to this on resistance. Why is that the case? Imagine the on resistance was very high. If the on resistance was high, it's going to limit the amount of current that's going to go to the ground. And therefore, the rate at which this voltage VDD is going to fall to ground is going to reduce. But if this on resistance is small, then the current is not limited very well. And therefore, there could be a large current helping this VDD to discharge all the way to ground. Similarly, what happens when you have the reverse case? Imagine you have a high to low transition. So originally the input was high, so the output was low. The PMOS was originally off, the NMOS was on. And now imagine that the input is going from a high to a low. Then suddenly the PMOS is now on and the NMOS is off. And therefore the output, which was originally at 0 volts, is now connected to VDD through the on resistance of the PMOS. So similarly, this process in analogous to the previous case is called as pull up, because the output node is now pulled up to VDD. And therefore, the input transition from 1 to 0 is now causing an output transition from 0 to 1. And it's very clearly, you can see that the time it takes for this node to charge all the way to VDD, again, is going to be proportional to the on resistance of the PMOS. So the speed of switching, so the speed of the output switching to low is going to depend on R on of the NMOS, and the speed of the output being pulled up to VDD is going to depend on the on resistance of the PMOS. In general, it's a good practice to make sure that the speed of the pull up and the speed of the pull down are the same. Because if these are not done, then you will have you could have a fast high to low transition, but a low to high transition and vice versa, which would cause a signal to distort, right? And you don't want that to happen. So therefore, you need the pull-up speed of the inverter to be the same as the pull-down speed, which essentially equates to having the same on resistance. So therefore, the on resistance of the NMOS must be equal to the on resistance of the PMOS. So how do we design an inverter which has essentially a PMOS and an NMOS to have a symmetric on resistance, which to have the same on resistance of the NMOS and the same on resistance of the PMOS, so that the time it takes for the signal to go from a low to high or high to low transition is essentially the same. So if we design an inverter that satisfies this condition, such an inverter is called as a symmetric inverter. So how do we design such an inverter? Now, during the on state of the transistor, we can show from device physics that the on resistance of the transistor is just inversely proportional to the current between the source and drain region. And therefore, the on resistance of the transistor is just proportional to, and here I've written the expression for the current between the source and drain when the transistor is switched on, which is what we discussed earlier. So it's 1 over mu n C ox Wn over 2 Ln times the gate overdrive of the NMOS. And similarly, the on resistance of PMOS is going to be proportional to 1 over mu P, the mobility of the whole Cox width of the PMOS over 2 times the length of the channel of the PMOS times the gate overdrive of the PMOS. And therefore, for a symmetric inverter, because we know that they have to have the same on resistance for the NMOS and PMOS, it just equates, it's just equivalent to saying that these two expressions are equal to each other. And if we can make some rules, so during the fabrication of the PMOS and NMOS and during the operation, if we ensure that both the gate overdrive of the NMOS is the same as the gate overdrive of PMOS, as well as the channel length of the NMOS is equal to the channel length of PMOS, which is set at the minimum channel length for a given technology node. For example, say the technology node is a 22 nanometer technology, then the minimum channel length will be around 22 nanometer. So in that case, the NMOS and the PMOS would both be set at 22 nanometer channel length. And this is a good practice because you want to always keep the channel length minimal to increase the speed of the transistor. And also the oxide capacitance, which is EOX by TOX, is also the same for the NMOS and PMOS. If we assume these things are valid, depending on the design of our NMOS and PMOS in operation, then substituting in this equation, we find that to design a symmetric inverter, the equation becomes the mobility of the electrons times the width of the NMOS is the mobility of the holes times the width of the holes, or the ratio of the widths of the PMOS and NMOS is just the ratio of the mobility of the electron mobility to the hole mobility. Now, in general, we can so we have this rule for designing a symmetric inverter in which the width of the PMOS over the width of the NMOS has to be basically mu n over mu p, which we can set as some value gamma. And therefore, if we design an inverter to have the width of the PMOS to be equal to gamma times the width of the NMOS, then such an inverter would be symmetric, would have the same speed of a 0 to 1 transition as a 1 to 0 transition. In general, this number, this mobility ratio between the electrons and holes, is a number typically between 1 and 2, depending on the technology node. Because in older technologies, it tends to be closer to 2 because the electron mobility in bulk silicon is around twice the hole mobility. But however, with things like strain engineering, by using a silicon germanium or a silicon carbide material for the source and drain in the transistors, it is possible to engineer the mobility of the electron, and therefore this number tends to be more closer to 1 in modern technology. That is, the electron and hole mobilities tend to be more symmetric. So now, if remember that we always want these things to operate as fast as possible. So we have set the channel length of the NMOS to be equal to the channel length of the PMOS, which is equal to the minimum length possible in that technology, which is the 22 nanometer. Say it's 22 nanometer, it's 22 nanometer. So if for a given technology, the width of the NMOS is set at its minimum possible value, say W, then for such a symmetric inverter, it can be called a unit inverter. So the unit inverter is the smallest inverter that can be formed in a given technology. So what is the definition of a unit inverter? So it's basically an inverter with the PMOS and NMOS, where the width of the NMOS is set at the minimum possible value in that technology. And because the inverter has to be symmetric, the width of the PMOS has to be just gamma times this W. So this would be a transistor where the NMOS width is W minimum, which is represented as W here, and the PMOS width will be gamma times W minimum. And this we will define as a unit symmetric inverter. And why we need this unit symmetric inverter is because any other inverter, any other symmetric inverter that we have would just be some multiple of this unit inverter. Because this W is obviously the minimum possible. So if you have an inverter which is twice as big, it just means that this W and gamma times W gets multiplied by a factor. For example, an inverter of size 2 would have an NMOS width of 2W and a PMOS width of 2 gamma W, right? So basically, as I mentioned earlier, the unit inverter is the inverter that's said to have the minimum size, which is the size of 1, which is the smallest possible symmetric inverter in the given technology. Any other inverter of any size beta is just, for some beta greater than 1, is just going to be, so an inverter of size beta is just going to be beta times this unit inverter, which in circuits is just represented by basically multiplying beta to the width of the NMOS and the width of the PMOS. And so this would be an inverter essentially of size beta. So now let's try to understand what this actually implies. So remember that so here I have shown you the unit inverter, and this is the inverter of size beta, which is just obtained by multiplying this factor beta, where beta is greater than 1, to the width of the NMOS as well as the width of the PMOS. So remember that the on resistance is proportional to 1 over for the so remember for these are symmetric inverters. So the on resistance of the PMOS is already equal to the on resistance of the NMOS. So the on resistance either for the PMOS or NMOS is basically going to be proportional to 1 over for the PMOS mu p Cox times gamma W over 2L times the gate overdrive in the case of the unit inverter. And therefore, it is very easy to see that in the case of the beta inverter, which is a size beta times the size of the unit inverter, this on resistance is just going to be multiplied by a factor. Sorry, this on resistance is simply going to be divided. Actually, this is wrong. This has to be divided by beta, because remember this term here is going to have a beta gamma W, so it's just going to be on resistance over beta. So the unit inverter will have on resistance. If the unit inverter has an on resistance of R on, the on resistance of the beta inverter is just going to be R on over beta. Similarly, if you look at the input impedance of this unit inverter, it's just going to be the gate capacitance of the PMOS in parallel to the gate capacitance of the NMOS. And therefore, the input capacitance is going to be the gate capacitance of the PMOS plus the gate capacitance of the NMOS. And this is basically the capacitance you would get for this corresponding to this particular width, the epsilon ox, which is the oxide dielectric constant, and the thickness of the oxide T ox, which is the same for both the PMOS and NMOS. So if Cn is the total input gate capacitance of the unit inverter, then the gate capacitance of the beta inverter, which is going to have everything, all the widths multiplied by beta, is just going to be beta times the capacitance of the unit inverter. So what we find is that the beta inverter is going to have an input capacitance which is going to be the beta times that of a unit inverter, and the on resistance of the beta inverter is going to be 1 over beta times the on resistance of the unit inverter. So what does that mean? That means that if you use a beta inverter to do the switching, the beta inverter is going to add more capacitance to the previous stage. And therefore, it's going to slow down the previous stage further. But for the next stage, it is actually going to speed it up because its on resistance gets multiplied by a factor of 1 over beta. And since beta is greater than 1, it means that the on resistance is basically reduced by the factor beta, right? So the beta inverter is going to slow down the previous stage and speed up the next stage. So now what we are going to do is we have talked so far about the driver itself, which is going to be our inverter. But before we proceed further, let us talk about the link that is connecting the transmitter to the receiver. Now, remember that looking, as I mentioned earlier, if you look into the receiver side, then all we see is basically a load capacitance because it is just going to be the PMOS and the NMOS connected in parallel, which is just some gate capacitance. So we are just going to observe some load capacitance at the input of the receiver. And because it's just either going to be some symmetric inverter or it is going to be some logical block. For the simplified transmitter and receiver that we will design, it is only viable when the links are relatively short and at low data rates. So the following few slides will talk about a simplified driver design without the use of SerDes, wherein the transmitter and receiver are just going to be inverters. And this kind of transmitter design only works in practice only when the data rates of the link is low or the link is relatively short. And when such an approximation holds, that is when the link length is very short or the link data rate is low, the entire link need not be modeled using an RLGC, need not be modeled using RLGC parameters of the transmission line, but we can basically use an equivalent RC model to model the transmission line. And this significantly simplifies the design of a transmitter and receiver side. If, however, the links are long or the links have higher data rate, then it leads to more bit errors and lower signal to noise ratio. And we need more exotic data transmission methods with the use of error correction codes, equalization, etc., which goes into the realm of SerDes, which is outside the scope of this simple inverter-based transceiver design. And as I mentioned earlier, for relatively short links with low data rates, we can completely ignore the link inductance because the link inductance is negligible, and therefore we can treat this entire link using an RC model. So remember, as our assumption is going to be the link length is going to be short, and it's going to be short compared to the to basically the shortest wavelength that you have in your transmitted signal, and also the data rate is also going to be low. And therefore, looking into the transmitter side, you're just going to see basically an RC network because the inductance of the link is going to be negligible compared to its capacitance because of its short link length. And therefore, looking out of the transmitter side, you just see a bunch of differential RC elements, which is also connected to the load capacitance, which is the input impedance of the receiver side. So now if you go into the circuit domain, what does this look like? So you have some input logic, which is now going to drive basically the parallel combination of the NMOS and the PMOS. And this could, for example, be a beta inverter that's going to drive this link, which is basically a distributed RC model, finally driving some load capacitance C load. So the question is, imagine that the input is going to have a 0 to 1 or 1 to 0 transition. How does the output transition actually look like? And how can we model this, right? So let's take a break now, and this will be continued in part 2 of this class. Thank you for your attention.